All right, welcome to the video covering the second law of thermodynamics and entropy. So I've split this up into the first page is talking about Carnot cycles. So a little bit more information about engines, and I'll talk a little bit about refrigerators, even though you're not responsible for it. And then we'll talk about entropy on the second page. All right. So this is something that you've seen before on the left right here. So this is an energy transfer diagram for a heat engine. The point of a heat engine is to maximize the work output given some heat that initially went into the system. So we define an efficiency. The Carnot cycle, C-A-R-N-O-T, is a particular cycle in the PV plane, a particular path, consisting of isotherms, so this piece and this piece, and adiabats. So the steeper pieces are the adiabats here. So isotherms and adiabats comprise a Carnot cycle. And a Carnot cycle is special because all of the heat exchange happens at a high temperature or a low temperature. So because we have the two adiabats, these two steep pieces, there's no heat exchange during those. So all of the heat that goes into the system happens right here for a heat engine, and all of the heat that leaves the system is right here at the colder temperature. So for this particular cycle, you can show that the efficiency you can write just in terms of those two temperatures, the high and the low temperature, and it looks like this. And actually, this is the best kind of engine that you can construct between two temperatures, between a high and a low temperature. So if you're, I'll just scroll down to this statement. So this is called the Kelvin statement of the second law of thermodynamics. So in this video, we'll talk about the second law of thermodynamics in several different ways. Once you start with one of these statements, you can prove all the other ones, basically. So this is our first statement of the second law of thermodynamics, and this is called the Kelvin statement. That's the one that has to do with heat engines. So the Kelvin statement is that it's impossible to build a perfect heat engine. So in other words, you're always going to have some waste heat right here. So this QC you can't force to be zero. I mean, ideally you want all of the energy that was heat and going to work right here, but it turns out that's impossible. And for any heat engine operating between TH and TC, between those two temperature extremes, the efficiency of your engine is less than or equal to the maximum efficiency, which is the efficiency of this Carnot engine, right, which is 1 minus TC over TH. These temperatures, by the way, have to be absolute temperatures. Notice how these are just T's and not delta T's. At first, I remember learning this, and this looks like a really random path to be the best possible thing. But actually, if you think of it, it makes sense that it's the best, because you're taking all of the heat right here, doing work, and spitting out heat all at this temperature. You can imagine if you took in some heat right here and you spit out some heat at some intermediate temperature, you can then take this and then put it into another heat engine and then spit it out at this temperature. So it sort of makes sense that all of the heat is taken at this temperature and extracted here for the best possible engine. And it happens to look a little bit funky on a PV plane, but yeah, the more you think about this, the more it starts to make sense. So Carnot cycles are super useful. You know, they're the perfect kind of engine. And we didn't talk about refrigerators at all. And you're not responsible for it on your homework, but I do kind of want to mention just some basic statements about refrigerators. So a refrigerator, the point of a refrigerator is to maximize the heat extracted from some cold temperature reservoir. So like the cold temperature reservoir would be the inside of your fridge, and the high temperature reservoir would be outside of your fridge. And this red system would be the working substance of your fridge. So there's another statement of the second law of thermodynamics called the Clausius statement, saying it's impossible to build a fridge where heat will just totally go from cold to high, to hot, from the cold temperature to the high temperature reservoir. So heat doesn't spontaneously flow from cold to hot, which makes sense. So in building a fridge, it requires you to plug it in. It's not going to work unless you provide some energy input as well. And in terms of, so then there's also a analogous statement to the second one as well. The best possible fridge is operating between two temperatures, is a Carnot cycle. So a fridge is very similar on a PV diagram, except it's going to be going in the opposite direction. So a fridge is going to go this way around the Carnot cycle. So there's a maximum possible efficiency of a fridge. We call it a coefficient of performance. So if we had more time, we would go into that. But mostly you'll just be responsible for the Kelvin statement of the second law and Carnot cycles and computing efficiencies. By the way, this is, you can set this equal to this. So if you know the Carnot efficiency, you can set it equal to W out over QH. That's still true. So this right here is true for any engine, for any heat engine. And if you know you have a Carnot engine, then you can also set it equal to this. And you know that that's the best possible efficiency. Okay, so we're going to another statement of the second law of thermodynamics, but it involves something called entropy. So entropy, so really it's defined that changes in entropy are defined first. So it turns out this quantity, so if you integrate dq over t, that's path independent. So remember we were talking about the path dependence of heat. If you go from some initial point to some final point in the PV plane, how you get from the initial point to the final point affects the heat involved. But the delta S for these two would be the same. This delta S is equal to this delta S. It's just the S final minus S initial. So the way to compute it is right here, the integral of dq over t. So this thing called entropy is a state function, just like internal energy was. So this also means that if you integrate around a closed path of this quantity, you get 0. Okay, so entropy involves heat exchange. So if you go along an adiabat, so I drew right here on the PV diagram, adiabats are isentropic contours, so same entropy. So if you go from one point on an adiabat and reversibly go to another point on an adiabat, the entropy change is 0. So all of those points are the same entropy. If you go from this point to any point up or right of this thing, you increase in entropy. So if you go straight from this point to another point, here these have ds greater than 0, and then down and left have ds negative. So entropy goes up if you go this way, and it goes down if you go the other way. We can write a formula for the entropy. So because S is a state function, it just depends on where you are in the PV plane. If I just had a dot right here, I could talk about what's the entropy of that point. And we'll see in class, we'll derive in class that we can write the entropy this way. So I guess this is delta S, because I wrote final and initials right here, right? So we don't really have a way so far. We will later when we talk about entropy on a microscopic scale, but we don't have a way of defining absolute entropy right now, just entropy changes. So this formula still doesn't say, what exactly the entropy is of this dot, but it'll say what, the entropy change between any two dots is with the final and the initial. Yeah, so again, this reiterates the fact that, if you go up, this term is 0, but the temperature goes up, and so entropy increases. And if you go to the right, well, if you go along a isotherm, so along this way, then the temperature is constant, but the gas or the system expands. So the V final is greater than V initial, and so the entropy goes up. Okay. Oh, and by the way, for an adiabat, these two will exactly compensate. So if we go this way along an adiabat, the temperature goes down, so this piece is negative, but the volume goes up, and this term is positive. So an adiabatic path has these two terms exactly canceling each other, and you'll explore that a little bit on your homework, maybe in an extra credit. Okay, so entropy is closely related to the second law of thermodynamics. So the delta S, as expressed here, is talking about the entropy change of the system, of whatever we're describing with this PV diagram. The heat must have flowed out of the system or into the system from some surroundings, and you could talk about the entropy change of that thing as well. What the second law of thermodynamics says is that when you add up these two pieces, you definitely get something non-negative. It's definitely greater than or equal to 0. It's greater than 0 if we have an irreversible process, and equal to 0 if we have a reversible process. So what this means in terms of the PV diagram, remember any path on a PV diagram was reversible. So if I draw something from like an initial point to a final point, and I'm going this way, the system's entropy goes down for this path right here, from this initial to this final. The system's entropy would be negative. That's okay. That doesn't contradict the second law of thermodynamics because the entropy of the surroundings went up. And they would be exactly equal and opposite for a reversible process. For an irreversible process, we wouldn't even be able to draw the path on a PV plane. We would somehow get from initial to final, but it would be non-equilibrium along the way. And in that irreversible case, even if the system's entropy went down, which is possible, and it would be the same entropy change for the system if we went from the same initial to final as computed here. So the entropy of the system still goes down by the same amount, but the entropy of the surroundings would go up, and it would go up by a greater magnitude, greater absolute value than this went down. Right? Again, from the second law of thermodynamics, it's positive. This change is positive for the universe if you have an irreversible process. So you have an intuitive idea of what an irreversible process is. It's something that's not approximately in equilibrium along the way. Any heat that flows between a non-zero temperature difference is irreversible. So if you think about water that's at room temperature and you stick it in the fridge, that is irreversible because you're not approximately in equilibrium. If the temperature of the fridge is 10 Kelvin less than the temperature of the water that you put in, the heat is going to flow out of the water and into your fridge. If you compute the entropy change of those two things, you're going to get something greater than 0. It's irreversible. So you're going to get some practice with this on your homework. I think you have an ice cube thrown into a lake, and you're going to compute the entropy changes, and you'll see that it's positive for an irreversible process. Okay, the last section, and this is very loosely based on OpenStax 4.7. It's sort of the same idea, but actually we veer a little bit away from the textbook. And I think we're not going to talk about this until the following week. But this will be relevant on your next homework assignment. On not your last homework assignment, but on the final exam. And this has to do with defining the absolute entropy, so not just the changes in entropy here. This has to do with entropy on a microscopic scale, and it's all about counting. So I'll put this here. All you're doing is counting. And it has to do with probability and just what the most likely situation is for something. So let me give an example here. Suppose you have four particles and you just stick them in a room. And you have an imaginary divider here that splits the room in half. And you're just counting like how many particles are on the left side of the room and how many are on the right side of the room. So you could look at this two ways. You could look at, so macroscopically, you just, you wouldn't be able to tell the difference between, like here the particles are numbered, but macroscopically you wouldn't be able to tell the difference. Like when each of these molecules, if they're made of the same molecule, suppose they're all the same type of molecule, when particle 1 hits the wall, you're not going to be able to tell the difference between particle 1, 2, 3, 4. So the macro state here is 2 particles on the left and 2 particles on the right. That's the macro state. The micro state is how many ways could we have arranged for different molecules to be in this state. If you think about this for a while, and you might want to work this out at the end of the video. It turns out there are 6 ways. There are 6 microstates. There are 6 ways of organizing these 4 molecules so that 2 are on the left and 2 are on the right. So you might want to figure out what are the 6 ways. In case this doesn't make sense, if you think there are fewer or more, you might want to work this out. So we use this capital omega letter to talk about the number of microstates that give the same macrostate. So if you throw 4 molecules in the room, this is the most likely situation here. It wouldn't be totally out of the question if 3 of the 4 molecules were on one side of the room and 1 was on the other side. All right, that wouldn't be too crazy. But it turns out if you're talking about a very, very large number of molecules, it becomes really, really unlikely for a significant fraction to be on one side of the room versus the other. It's always going to be very close to half on both sides, just by counting, just by seeing like how many microstates correspond to that macrostate. And there's a way of keeping track of, and there's a way of defining entropy in terms of these microstates. So if you just define entropy as some constant with units of joules, units of energy per temperature, or SI units of joules per Kelvin. So we need some constant that has those appropriate units, and then take the log of the number of microstates. That quantity acts a lot like entropy. It is a good starting point, actually, for entropy. And when you take an upper division course on statistical mechanics, this is your starting point. Oops. This is your starting point for what entropy is. And then starting from this, you can actually derive all of the other statements of the second law of thermodynamics. So historically, we kind of started with the Clausius statement and Kelvin statements and talked about heat engines. And then we moved towards this notion of entropy in the later 1800s and used this in the early 1900s. But really talking about statistical mechanics, this is maybe the more appropriate starting point. So we want to expose you to this way of thinking about entropy as well. So lots of ways of thinking about entropy in the second law in this final chapter. Okay, that about does it.